So over these last few lectures, we've been looking a lot at taking a rate of change function and trying to get information about the original function, taking velocity and trying to get information about displacement. Or in general, just taking a derivative and trying to get information about the original function. Okay, so this gives rise to the idea of an antiderivative. Now, first of all, I just want to mention that the notation gets here a little bit funny because they are using F, using capital F and lowercase f in this definition here of an antiderivative. So it can get a little funky when I try to explain it because it doesn't, when I say F, I have to distinguish capital F or lowercase f. Okay, so if the derivative of capital F of x is lowercase f of x. Okay, so we're kind of assuming that the derivative of capital F is lowercase f. Okay, that is f prime, capital F prime is lowercase f of x. We call the capital F function the antiderivative of f of x. All right, so all right, let's just the notation is weird because of that. So the capital F and the lowercase f mean different things. So watch the case of your of your letters here. But it's not a complicated concept. All right, the antiderivative of f of x equals 2x. What is the antiderivative? So we're just asking, what function would we need to take the derivative of in order to get 2x? All right, so another way to rephrase this question is just, what function has a derivative of 2x? All right, well, you've had enough experience with derivatives by now that you know that if I have x squared and I take the derivative of it, it's 2x, right? So the antiderivative, or an antiderivative, what I should say, not the antiderivative, but an antiderivative of 2x is x squared, because the derivative of x squared is 2x. So, the function, the antiderivative, right? The function that has a derivative of 2x is x squared, okay? So is this antiderivative unique? Well, no, you probably already guessed that. No, it's not unique, because if I took the derivative of, say, x squared plus 8, that also has a derivative of 2x, right? Because the derivative of x squared is 2x and the derivative of 8 is 0. So that also, x squared plus 8 also has a derivative of 2x. So x squared plus 8 is also an antiderivative of 2x. We could also look at, we could look at x squared minus 6, right? That also has a derivative of 2x. So another antiderivative of 2x could be x squared minus 6. And we could find any number of functions, right? If we just change this constant, then we can find all kinds of functions that have have a derivative of 2x. So in general, we can say that the antiderivative of 2x is something that looks like x squared plus a constant. All right, just some constant c. We don't really know what c is unless we're given some more information. All right, so that takes care of that example. We're going to go back to looking at graphing antiderivatives here in the next video.